For this problem, a fan is to produce a constant airspeed of 40 meters per second throughout the pipe loop shown in the figure below. The 3-meter diameter pipes are smooth, and each of the 4 90-degree elbows has a loss coefficient of 0.30. We're asked to determine the power that the fan adds to the air. This problem will bring in the relations for pressure drop due to viscous friction and to fittings, and also the relation between pressure drop, flow rate, and power. The basic relation is the energy relation with the head produced by the fan and the head loss due to friction and fittings. In terms of head, the energy equation is the pressure at some point over gamma plus the velocity over 2g plus the elevation at that point plus the head produced by the fan equals the pressure at another location over gamma plus the velocity squared at that location over 2g plus the elevation plus the head loss between the two positions. We'll select locations 1 and 2 at the same place so that the pressures, velocity, and elevations are the same. Let's look at our figure again. If we'll pick, for example, a position 1 here and a position 2 here, then we'll be getting all of the losses due to the pipe and the fan power, and we come back to the same location. So if we pick the same location for 1 and 2, we'll have the pressure at 1 equals the pressure at 2, the velocity at 1 equals the velocity at 2, the elevation at 1 equals the elevation at 2. So the energy equation reduces to that the head that must be produced by the fan equals the head loss due to friction and fittings. We'll now compute the head loss. The expression for the head loss is the sum of two terms. It's the friction factor plus times the flow length over the diameter plus the sum of the loss coefficients times the velocity squared over 2g. The friction factor is a function of the Reynolds number and the relative roughness of the pipes. To compute the Reynolds number, we need the properties of air. We'll use table B4, and we'll pick the temperature at 15 degrees Celsius. And the density is 1.225 kilograms per cubic meter. And the viscosity is 1.8 times 10 to the minus 5 newtons second per square meter. So we can compute the Reynolds number as V rho d over mu. The velocity is 40 meters per second. The density is 1.225 kilograms per cubic meter. And the diameter is 3 meters. And the viscosity is 1.8 times 10 to the minus 5 newtons second per square meter. And the Reynolds number comes out to be 8.17 times 10 to the 6th. So the flow is turbulent. It's also stated that these are smooth pipes, which means that the relative roughness epsilon over d is 0. So we'll use the Moody chart, which is the plot of friction factor versus Reynolds number. For smooth pipes out in the turbulent regime, the curve looks something like that. If we go into the Reynolds number of 8 times 10 to the 6th, we'll come up with a friction factor of about 0.0083. And again, it's not too important to be very accurate with this. 2 significant places is enough. We can then compute the relative terms in the head loss. First term is this F L over D, which is 0.0083 for the friction factor. The total length of the pipe is 60 meters all the way around the circuit, and the diameter is 3 meters. So this first term comes out to be 0.17. The second term is the sum of the losses, and there are 4 elbows with a loss coefficient of 0.3, so this comes out to be 1.2. And this term is about 7 times that term. So for this problem, the head loss due to the elbows is going to be about 7 times that due to friction along the smooth walls. The total head loss then is the sum of the 2 terms, F L over D plus summation KL times V squared over 2G. So that's 0.17 plus 1.2, and the velocity is 40 squared meters per second squared over 2 times gravity, which is 9.8 meters per second squared. And the total head loss comes out to be about 112 meters. So now we'll compute the fan power. The fan power is computed, W dot, as the specific weight of air times the volume flow rate times the head loss. The specific weight of air will compute from the density, rho g. The density was 1.225 kilograms per cubic meter, and the acceleration due to gravity is 9.8 meters per second squared. This comes out to be 12.0, and its units are newtons per cubic meter. The volume flow rate will compute from the area and the velocity. The cross-sectional area of the pipes is pi over 4 times the diameter, which is 3 meters squared, and the velocity is 40 meters per second, and this comes out to be then 283 cubic meters per second. So the power for the fan is then the specific weight, 12.0 newtons per cubic meter, times the volume flow rate, 283 meters cubed per second, times the head loss, which was 112 meters. And this comes out to be then 3.8 times 10 to the 5th. The units, Newton meters per second. And a Newton meter per second is a watt. So this is 3.8 times 10 to the 5th watts, or 380 kilowatts. Okay, so in this problem, we've learned how the major losses, which are due to pipe friction, and what are called the minor losses, due to the loss coefficients, combine to produce the head loss, and then how this combines with the flow rate to produce the fan power required.